Okay, I think this thing is on, and it's 12 o'clock, so it is time to start class, although it feels a little odd to do so from my house. But anyway, you know how it goes. If you are listening online, you are welcome to use the chat window to ask a question. There may be a little bit of a delay while I get your question, but you are certainly welcome to do so. And I'm going to type something real quick. There, you should be able to see me say ask a question here. But we're going to start today with lecture 5, which is our kind of the end of our IRT and item factor analysis lecture. So I have the slides for lecture 5 up in this window here, and we're going to go over a couple of the parts of IRT that make it interesting and useful. You can see all my markings and so forth. But in the last couple times, we have discussed several different ways of discussed how we end up getting models to work in Lavon. We discussed what the model parameters mean. I can barely hear you. Let me see if I can turn the volume up. Hang on just a second here. Let's see if this works better. Can you hear me better now? Well, we will find out. 1 second here. Okay, let's try that. Hopefully that's a little bit better. If you can hear me, let me know. Okay, great. You can hear me with headphones. Fantastic. All right. Thanks, Katie. Thanks, Razag. Appreciate it. Good to see you, I guess. Thanks for bearing with me. All right, where we left off last time, we were involved with talking about how to use Lavon to get, I think, Ahmed and Shada, thank you very much. We were working with Lavon to get model parameters for IRT, and we'd seen that for the most part, things were mostly the same structure-wise as CFA, with the two big differences being instead of having an item intercept, there's now an item threshold, and instead of having a residual variance, there's nothing. It doesn't actually work like that anymore. Okay, there's no, no distribution, no part of the distribution that would go with residual variance. So, what we're going to start with today, we're going to talk a little bit about the kind of the wrap-up of IRT, the things that we didn't have a chance to get to yet. And part of that involves a couple additional models. Let's see here. So what we have been doing in Lavon, and the example for Lavon, examined a 1 parameter versus a 2 parameter model. And if you remember the 1 parameter, that was what I'm calling analogous to the Roche model. The 2 parameter model, the 1 parameter model, you had a common discrimination parameter, or factor loading or slope. The 2 parameter model allowed that to be different by each item. You get to hear the dogs bark outside my window too. And so now what we have, there are a couple other models that you'll find for binary data. Of course, none of these work in Lavon, but you can find them in the VERT package. You can also find them in M+. So just wanted to tell you about these because they occasionally pop up. The first is the 3-parameter logistic model. Now again, this is not as much a probit, but you could swap out the part that is probit over here for the part that's a logit, this e to the something over 1 plus e to the something. If we switch that with a logit, then we would probit, we would end up getting the same thing. But what this ends up doing is it provides what's called a C parameter. So we have the A parameter, which is discrimination, the B parameter, which is difficulty per item, and then we have the C parameter, which is supposed to be sometimes called the guessing parameter or the pseudo-guessing parameter. What it does is it provides a lower bound of probability for the item response that is independent of theta itself. So if you remember that S-shaped curve that we had on the next slide here, this is slide 34, that S-shaped curve that we had before, it would have an asymptote at 0 as theta went down to negative infinity. What the C parameter does is move that asymptote from 0 but up some. So for instance, a C of 0.2 means the lowest probability a person can get on that item, of answering that item correctly, is 0.2. So why this is used, often we find this used in educational measurement, where we have sort of ability tests or aptitude tests where they have multiple choice answers. So there's some non-zero probability that a person will answer the item correctly, regardless of how low their trait value happens to be. Oftentimes you can think, oh, is that going to be, if I have a multiple choice question and I have 4 options, is it going to be, is the guessing parameter going to be about 0.25? In practice, it's not quite like that, because often the options themselves are pretty easy to eliminate. So we often find guessing parameters usually higher than the number, 1 over the number of options on a question. But this is what we use it for. More often than not, what I feel like the guessing parameter starts doing is it starts to mask whether or not you have other dimensions present on your item. So sometimes the C parameter really functions as, it's kind of like the residual covariance did in factor analysis, where the kind of putting a residual covariance in makes the model fit better, but it doesn't necessarily tell you anything great about what you're measuring. In fact, it actually weakens your measurement argument. The guessing parameter is sort of that way. It sort of allows the model to fit a little bit better. It doesn't necessarily weaken your argument, but ultimately guessing is sort of an odd thing, particularly for items that don't necessarily have multiple choice tests. So that's the 3PL. I'm not, sorry, Razag has a question. Does this mean that the distractors are poorly written? Oftentimes with the 3PL, often in a lot of multiple choice tests, some of the distractors are poorly written. Not all of them, but some of them are. And so even a person with a low ability theta, low level of the trait, let's say it's math, for instance, can eliminate 1 or more of the distractors pretty easily, in which case the C parameter will be higher than the 1 over the number of distractors. Okay, so again, 3PL, something that you can do in M+, something that you can do in MERT, but oftentimes we don't see that in a lot of non-achievement, non-aptitude tests themselves. I will say this, the 3PL is the model that is used for the GRE test. It is the model that is used in a number of state tests themselves. Let's see here. Question comes in. If the first graph, the one in the upper right-hand area on the slide, shows items with lower discrimination, how can you tell which item is the worst of those on the graph? That's a good question. So the graph up at the top right here, the top items have have lower discrimination but lower difficulty, and the bottom have higher difficulty. And so let me back up here. So what makes a good item is still not necessarily an item. It all depends on where your level of the trait happens to be. So if you are somebody who is, but ultimately a good item is an item where you're right where the steepest slope happens to be, that line where we talked about the line that's tangent to the curve, where that happens to have its steepest slope. Now before we talked about that being at the item difficulty, with the 3PL, because that lower asymptote changes off of 0, it's just slightly above the item difficulty where the steepest slope happens to be. But that's where the item is best. And so what makes a good item depends on which level of theta you happen to be. So for somebody who has a -2 for theta, none of these items would be very good, although the items that have a little bit steeper curve, which are the blue ones, do a little bit better than the items that are in pink and maroon here. Likewise, if you're too high for theta, they treat you all the same as well. They're not necessarily any different. But ultimately, the items that are best are the items for each item is going to have a location that is best for each type of theta itself. And that actually brings us up to another point in just a moment that we're going to get to. Ultimately, also, if you're going to compare items that have the same difficulty, so let's say you have items here, you have an item that has -1 for item difficulty in the blue curves, and here you have an item that also has -1 for item difficulty. Those items, again, now if they have the same difficulty, the ones that are less discriminating, the ones that have the same difficulty, tend to be worse items. But again, that also varies based on how high the C parameter is. Right? So in general, what makes a really good item is a C parameter that's really small, or 0, and a very high discrimination. And that item, when that happens, that item is very good for people who are close to where item difficulty happens to be. Does that help? Hopefully it does. So I'm going to learn to pause a little bit more because of the delay. Okay. So there's another model out there, which is just psychometricians behaving badly. If you notice, before, the C parameter shows up at the outside of this other probability function. So in the blue box, that blue box did not appear when we had the 2PL. So we put the C parameter there, and it shows up as C plus 1 minus C times what looks like the 2PL. The C parameter itself, because it's out here by itself, that shows the lower asymptote. And then the rest, 1 minus C, represents the rest of the probability with which the IRT function can work with. Well, someone happened to note that, hey, that 1, that's an upper asymptote. Why don't we just go and put a parameter for that too? And there, sure enough, there's the 4-parameter logistic model. It is the model that has an upper asymptote and a lower asymptote. And this is upper asymptote is really hard to describe. Some people have called it as carelessness. I think it's, I don't know. I don't see a good use for it, so I don't typically talk about it much. So we're just going to, it does exist, but that's good enough for us. So any other questions about these additional IRT models that we won't be trying out in class, but that do exist? So the next part of what we talk about with IRT comes from, well, model identification. We already talked before that model identification is the same. Sometimes we call this anchoring, but that's not exactly the same. But really what we want to talk about is reliability. In item response theory, what we quantify reliability as is a little bit different than what we quantify it in CFA and classical test theory. Now, as you recall, CFA, we had reliability. Actually, both CFA and classical test theory, whatever measure of reliability we happened to build, it was the same for every score on the test. And in IRT, information is typically the term that we describe instead of reliability. And that talks about the measurement precision, the amount of precision that we get from each item or for a test for each value of the trait that we may estimate, each value of theta. So the IRT model with information, it is not necessarily the same for every item of the test. Now there are ways that you can try to get it to be as close as possible the same for every, not necessarily the same for every score that comes from the test. So let's just sort of remember here. In CFA models where we had continuous outcomes for our items, item-specific information is rarely referred to. However, we could have done that. Could have referred to it, we could have estimated it. In fact, it's somewhat akin to the idea of the standardized coefficient, the standardized factor loading. The bigger the standardized factor loading, the bigger the item information. But the actual number that we would come up with if we were to estimate it ourselves is found from taking the unstandardized loading and dividing it by the error variance. I'm highlighting this part of the slide right here. So what this information represents is how much of the variance is true for an item itself. So how much is shared with the trait relative to error. And because if you look at the information function in CFA, there's no trait, there's no factor, no theta, no whatever you want to call it, it's going to be constant across every trait level. So that means that items all contribute one number to your total information, and that total information is flat across the entire scale of the trait itself. So we don't often talk about it because it's flat. It's sort of not important in some respects. But if we wanted to try to make our test be more informative, right? If we wanted to increase the reliability, how would we do so? we would find items that had larger information coefficients. And again, by larger, we would say they would have a larger unstandardized loading squared divided by or your error variance, residual or unique variance. So basically, we are looking for items that have stronger factor loadings. So information itself, each item contributes a piece of information. And in CFA, again, it's that one number that comes from unstandardized loading divided by the error variance. If we want to talk about total test information, or better yet, how reliable our test is for each level of theta, the way we would do that is to sum the items, sum the information across the items. So here, information again is the unstandardized loading. In CFA, unstandardized loading divided by error variance. We sum that up and we get what's called the test information function. So this test information function, again, we never talked about in CFA because one number would characterize it. It's this flat line itself. So that was CFA. And again, never talked about it. Wasn't a really big deal. But IRT, to do IRT, we end up having a little bit differently. Actually, here's the CFA model again. Here are two items. We have y6 and y1. We can tell here that y1 seems to have a bigger slope, but the information for each item doesn't just depend on the slope. It's the slope squared divided by the residual variance. And sure enough, for this item, item 1, if we thought the residual variance was 1.53 for item 1 or 1.67 for item 6, we would get at an information statistic here. It would say item 1 would actually have more information than item 6. So here, basically, item 1 would be a more informative item across the entire test itself. So question, how is the test information function useful? In other words, what does it tell you or the reader? The test information function is useful, not so much in CFA because it's perfectly related with reliability. But it's much more useful in IRT because it's going to not look so flat. So hang on just a second and I will show you that coming up here. So moving to the next slide, 39. Test information in IRT models is a little bit different. If we have a test information function, we could always calculate reliability by taking information divided by information plus 1. Now that assumes that the variance of the trait is 1 to make that. So if we want to talk about what reliability for a given value of the trait happens to be, we have a test information function. We take a look at the trait on the like the x-axis, and we go up to the information value. We can convert it to a reliability for the latent variable this way. Now, do you remember? If you remember, reliability always comes from this formula that basically the proportion of variance in the trait that's due to variance in the factor itself. So that's where this is coming from. So oftentimes, though, in IRT, we rarely speak of reliability. We mainly only speak of the standard error for the trait itself. So that's where that comes from. Also, the thing about reliability that gets confused in CFA is that CFA reliability, there's all these different types. If you remember, there was Spearman-Brown and alpha and omega. And then there was some reliability for the trait itself. The reliabilities of Spearman-Brown, alpha, and omega are the reliabilities for the sum score. So even if you did CFA, if you provided scores by adding up a bunch of the items, that reliability that you would get from an omega, an alpha, or a Spearman-Brown would be the reliability for that sum score. However, if you would give a person their factor score, the reliability itself would have to come from this formula, which is essentially the true variance divided by the true variance plus the error variance. And what do we talk about here for each of these? The true variance is the variance of the trait itself. This is the kind of the variance of the factor. The error variance is the standard error of the factor score squared. So that's how that comes from for reliability, where that comes from. So what's going to happen is that we're going to see in IRT that our information function no longer, each item is not going to have a flat line. So here's a comparison of the two features. In In IRT, we have these curves right here. We talked about the curves being the best, or the item being best for somewhere near where the item difficulty happens to be. At the top, again, the top graph on the left is the item characteristic curve from a 2-parameter IRT model. The top graph on the right is the CFA item characteristic curve. There's no curve to it; it's just a flat line. Again, the trait is on the x-axis, and the predicted response is on the y-axis. So in this case, for CFA, that's the actual value of the score itself, whereas in IRT, that's the probability of a 1, essentially, for that item. So if we convert this into the test information function, you'll see in CFA, item 1's test information function was real close to 1, which is what we had talked about in the example just a few slides ago. Jihong asks, do items in the Roche model have the same amount of information? Items in the Roche model, yes, the height of the information curve is roughly the same for each of them. It's just where the information is centered varies. So here in the bottom, if you take a look at these curved lines, this is for 2 hypothetical items, item 3 and item 4. Item 3, both of these are 2-parameter logistic model items. So the lower asymptote or the C parameter is 0. In item 3, the difficulty is at 0 and the discrimination is at 1. In item 4, the difficulty is at 0 and the discrimination is at 0.5. And so if you take a look at item 3, the peak curve here, this is the amount of information that item is telling you for any given value of theta itself. And you know there's a peak value of information, and that peak happens to fall exactly at where the item difficulty is. In the 2PL model, the item difficulty is where the maximum amount of information, where the item is most informative. So that means people who take this item get a lot more information about theta given to them if their theta is 0 than if their theta was higher or lower. Now, item 4 also has the same peak amount of information, and that happens where theta is 0. However, because the A parameter, or the discrimination parameter, is lower in item 4, you'll see that the height of that line is lower relative to item 3. So ultimately, if you were to talk about which item might be better, item 3 would be more would give you more information about the trait than item 4 would. And actually, you'll note that there are sections of theta where item 4 starts to beat item 3, where it's above the pink line itself. But those sections are at the tails of the test itself. So that's what an IRT item information looks like, function looks like. So each item has its own information function. And if we have a bunch of items like we have here, I'm sorry for my formatting being all off, but here's a bunch of items with varying levels of A and B. And here are the item information functions with each of them. Right, you see right here, again, there's no C parameter involved in these items. So the items that have the same value of discrimination will have the same peak for information. It's just the location of those will vary by the difficulty. So what am I talking about? Item 2, item 4, item 6, and item 8 have a discrimination of 1. Item 1, 3, 5, and 7 have a discrimination of 0.5. So the lines that have the higher peaks here, that's the even items, 2, 4, 6, and 8 with that higher discrimination. The value where that peak happens to fall comes by the value of the difficulty. So you might have a discrimination of 1 and an item difficulty of -1 here. So that peak is right at about -1 for the item 2. But then item 4 has a difficulty of 0. Item 5 has a difficulty of 1. Excuse me, item 6 has a difficulty of 1, and item 8 has a difficulty of 2. So here, each of these items has a different item information curve, and that's telling you that each item gives you more information about different levels of where that trait happens to be. So if we sum all those items together, we get what's called the test information function. So this blue line right here would be the sum of all the item information curves for each value of theta across all of the test itself. And so the test information is in blue, The red line represents the corresponding standard error for theta, for each point along that, along the trait itself. And the standard error is found by taking 1 divided by the square root of the test information. For those of you who are into more technical versions of statistics, that what we call information is really something that's also called Fisher's information, which comes from, it shows up in maximum likelihood, and it comes from differentiating the likelihood function. Too much calculus, too much information. You can just ignore that if you're not into that. But that's where the 1 over the square root of information comes from, gives us the standard error. So basically what we're talking about here is that for each value of theta, a different standard error might show up. And you'll see this test information function is fairly flat in information, somewhere between -1 and +1.5. A long range of the theta distributions pretty much have the same reliability. We would call this a fairly flat test information function. But depending on what your purpose of measurement happens to be, the test information, there is no real single ideal test information function. So here are a couple examples. This is not necessarily so good. This is a test information function over here. The highest part it gives you is somewhere around -1. And what you'll see is the value of information only goes to a little below 1.8. Remember, an information value of about 4 gives you a reliability of 0.8. So this is telling you right here, even for the people who are at the part of where the test is measuring them most reliably, their reliability is not going to be all that high in total. Here's another type of test information function, something that's very low information until you get close to a cut point. So maybe this is a licensure test, or maybe this is a high school graduation test. You want to be really sure and really precise right around that cut point, because people who are further and further away from the cut point, you know the decision for them. They will either pass or they'll fail. The people right around the cut point sort of falls into that level of where things might be a little bit gray if you add in information itself. And if you're into classifying people, there's another class of models. This is what I do my research in, called diagnostic classification models. I gotta throw that in just a little bit, but that's where that ends up going. But how do you improve your test? Well, we said this before. In classical test theory, you need more items. Which item? So long as they have a positive correlation with the other items, it's fine. Any item is exchangeable. In CFA, the question is, you want an item that has a better standardized loading or a better information function. But it's not necessarily for whom, though. It's how much better does that item happen to be. But for IRT, the question then it becomes, how much better is each item and for whom? Because that information function has a peak that's not the same for everybody. You end up getting when you add an item to the test, some people are measured more precisely than others. But in respect to this, if I go back a little bit, or if I go forward to this item information, let me go back to the test information curve real quick here, which was right here. What you'll end up seeing oftentimes is this is why people who are up toward the ceiling of the test and people who are down toward the floor of the test are the hardest to measure. Because these, oftentimes, those are kind of toward the tail of where the items aren't so difficult usually that they're above 3 or below -3. And what do I mean by that? Well, let's think of this trait as being standardized. If it had a mean of 0, right here in the middle, and a standard deviation of 1, that means most of the people are going to be within -3 and 3. I think 99% of the people are going to be there. But as you get further and further along, it's going to be very hard to get estimates of difficulty, because ultimately a difficulty very close to -3, which would be a high information item for people toward the floor of the test, that difficulty is hard to estimate, because there's so few people getting that item incorrect. Right? You think of all the people who are right about -3 or lower. Those are the ones that have a bigger than 50% chance of answering the item incorrectly. It's hard to do. Same thing. The same flip of that at the ceiling of the test as well. So what you can do, though, with the test information function, though, is to build tests that specifically tailor to the needs that you're trying to build them for. And again, this gets more into a measurement class than what we do with SEM, which is SEM we want to go usually take our thetas and predict something else. Here, the test information functions, if you think about it, maybe this is your test pool, maybe you want to measure people toward the high end of the test itself. Well, you might not take all the items. You might just take a few of the high information toward the high end of the range of theta and put those on a test. And that's what this next slide is trying to say. That's what an adaptive test tries to do. Where basically, if you take a look at these curves at the top, these are fixed 20-item tests, each with a different level of, this is the standard error of measurement. So this is kind of information, the inverse of information squared. This thing right here, these tests, for fixed 20 items, you see that trend that we normally see, that the top part of the test and the bottom part of the test are really hard to measure. They have bigger standard errors of measurement. Here, for the adaptive test, though, because what an adaptive test tries to do is it will go and basically every item that you take of the test, it recalculates what its best guess for your theta happens to be. And then it grabs the item that's most informative for you, subject to some other type of decision rule so that items don't get what we call item exposure, where they don't get used more frequently than others. But ultimately, with that type of control, you're able to always give people the same type of items, or the items that are most informative to them. And Shada has a question. Is this correct? There are a few people getting high difficulty items correct, theta equals 3, and few people getting low difficulty items wrong, theta negative 3, so you get minimal information from those items. Really, it's not that you're, it's not necessarily that it's correct that you're not getting much information. It's that it's really difficult to find items where you're getting so many people or so few people getting them correct and incorrect. If you think about it, if you have an item with a difficulty parameter of 3, the people who are at 3 standard deviations above the mean will have a 50-50 shot of getting that item right. So you'll have to have a really, really large sample just to find enough people to find stable estimates for the parameters themselves. So it is possible to do, but it's more the fact that it's just a numbers game. The sample size goes up considerably just to be able to get good estimates. I hope I answered your question with that, though. So anyway, this is where the idea of adaptive tests started to come from. The adaptive tests, though, have their own problems. Depending on how items are selected, one of the things that GRE, so the GRE went adaptive in, I believe, 1998, because I made sure I took the GRE, that was the year I took it, and I made sure I took it on the pencil and paper form. So I figured the translation from pencil and paper to adaptive would be a little weird in the first few administrations, so I wanted to go with the format I knew. And sure enough, so the original method that ETS used to select items for the adaptive GRE made it so that a number of items were routinely, the chance of getting just a few items turned out to be very high. So what do I mean by that? So let's imagine you start off, you take the first item of the test, it gives you a random item, and it tries to calculate theta. There's only so many theta values that go after you've taken 1 or 2 items of a test. And so because of that, depending on how you select the next item, you may be giving the same item to the entire group of people for the most part. And that's what had just happened. The GRE, shortly after it was mapped onto adaptive, you found people who were able to basically take the test and then come back to kind of a debriefing room, depending on, this happened in a lot of different places, several different countries did this, where they would have people taking the adaptive GRE, and at the end of the GRE, they would have people come in and just write down the number of items they could remember from the test. And sure enough, with not a lot of time, with not a lot of people remembering not a lot of items, I think it was something along the lines of 25 people. If 25 people could all remember 5 items, they were effectively getting the answer key to study from most of the people taking the GRE. And so this is where you'd start to see certain countries where English was not the primary language, but their English scores in the GRE were beating the other countries where it was. was all sorts of interesting and aberrant behavior that happened. This was sort of shortly after the year 2000. People really recognized it. And so now what you find is the GRE is something called phase adaptive, where they give you a block of items. That block of items effectively is like a mini test with its own test information and function. And then you get a calculate. You calculate after a person's done with that block. Then you calculate their theta, and you assign the next block that's closest to theta in terms of information function. So it's a little bit different. Within the block itself, they can rearrange items. They can make it a little bit so that things are a little bit more random. And I think that they've found that it's much easier going with it then. So let's see here. So the thing about it is, so IRT, when it comes to information, some people think it's great, it's fantastic, because if you look at this comparison chart here, you can focus your reliability on certain people, a certain range of theta itself. But it's sort of turning lemons into lemonade. This graph that you see here, if you were to go and calculate most information functions for items that are doing CFA, let's imagine we take a Likert style item, one that truly has categories, but we fit a CFA model with it. We get an item information function like Y1 here, which is much higher than either item 3 or item 4. And what ends up happening is the continuous items, truly continuous items, and they truly function like that, those items tend to have a lot more information than the binary items themselves. And if you think about why that is the case, if you could create a truly continuous item that had any number of scores, it could be very precise about telling you what a person does and doesn't know. Whereas a binary item, all you get is a 0 or a 1. Either a person got it right or a person got it wrong. So IRT is the sort of the best way moving forward of taking that and understanding where a person might be. But if you were to go, if you could measure something, if you could create an exam any way that you'd want to, if you could come up with truly continuous items, those items have the potential to pack a lot more information in them than binary items certainly do. So it is an interesting feature of what we do. It's sort of like IRT has a really good marketing campaign to sort of put everything together. Okay. So another thing that we can do with IRT and CFA is that because items and people are sort of put into different dimensions, we might have a set, maybe there's 6 items at time 1, another 5 items at time 2, another 5 items at time 3. But people who take the test at time 1, at time 2, at time 3 get the same core of items, 4, 5, 6. This is something that we'd call a linking design, where we try to basically link the scale together across time so that we can compare people's theta values from time 1 to time 2 to time 3. So to do that, to do linking in IRT and CFA, you have to effectively, one of the easiest designs to do so is to build forms that have, so item like form 1 here, 4, 5, and 6, this is sort of, if you can imagine, this is where their peak information happens to be. So this is time 1, this form might be something measuring the low end of the theta scale. Whereas at time 2, it's up a little higher, and time 3, it's up a little higher. This is sort of linking scales together across time using a block of common items. This is one of the nice things that you can do with tests like this. Let's see. So another nice benefit of IRT and CFA is that if the model fits, then the scale of theta is linear or interval level. Well, that's sort of true. The bigger problem is it's interval level, but there's a lot of error in theta itself. So anyway, these are good approaches. They do very well themselves. Any questions about IRT or anything that we're getting into right here when it comes to test information? Learning to pause a little bit longer. That's the thing that is the hardest for me today is normally I look at you while I'm teaching and kind of gives me an idea of how long or how short I can spend on each topic. But this is shooting in the dark here. So if you have any questions, please don't hesitate to put them in the screen. And certainly, I think we'll hopefully be having class on Thursday in class, and you can always ask me then as well. So I want to go back to example 5, because example 5 shows the test information function at the top. Here is the setup for example 5. We had 7 items that we dichotomized, which, again, not something we should really do. But those items are dichotomized so that we would have a, just to show how IRT would work. And so here, let me zoom in on our studio. Actually, I think you can see it better if I do it that way. So example 5, again, we have 635 older adults. Sure enough, Levon doesn't give you any of the information about test information. Doesn't give you any information about item information. You sort of have to create it yourself. But the MERT package does do that. So if you're interested in building a scale with IRT, the MERT package is really the best one to use, I think. But if I scroll down, the very first part of what I did in this example was to use the MERT package. And at the bottom of it, where I had these items themselves, I created a bunch of plots. And let me see if I can find them. Here we go. Those are the item characteristic curves. But here is the test information function. So now we can put this in a little bit more context. This test information function has theta on the x-axis here. On the y-axis, we have the information given by the test for that value of theta. Now these are 6 actual items. Let me zoom in a little bit so you can see this. And the information is a peak somewhere just below 0. So remember, theta we estimated with a standardized factor. Standardized latent variable method, so we were able to see that its mean was 0 and its standard deviation was 1. So basically, we're thought that our test is most informative for people who are somewhere about a half a standard deviation below the mean. And that looks great. And then shortly after 0, you take a look at our test information, it crashes. We have very little information at high levels of the trait. And also, we have we do have a little bit of information as we get lower and lower, but again, toward the tail or the floor of the test, we also have very little information. Now, remember that formula to calculate reliability from information. If you wanted to talk about a person's reliability at the maximum value, it'd be information divided by information plus 1. So that's reliability at 0.98, 0.99 is really reliable for people right there. And it's actually very reliable for everybody. You know, if you talk about like a 0.8 standard or where a cutoff should be, pretty much anybody who is between, so that would be an information of 4, by the way. So anywhere in between, somewhere around negative 1.6 and positive 0.25 has a 0.8 reliability or higher. And you'll note with this test, the items of the test, which are at the top of the screen, these are basic functioning items. This is an older adult sample, and then we're trying to measure how well a person can do in terms of day-to-day functions themselves. Shada has a question. So this would be an example of a tested information shape demonstrating a cut point of 0.5. Yes, it would be very much like that. If we had a cut point at 0.5, and we were trying to say people who above this level might not need much help, that would be what we would do with this. So anyway, this is the test that is built to measure sort of older adults who might need a lot more help getting through day-to-day tasks. Yes, that's right, negative 0.5, pardon me, yes. And those tasks, they tend to fall so that those items are, if we go back up and look at them real quick here, you can see the proportion of people who are able to do that. So 64% of people in the sample are able to do housework, 84% can do bed making and so forth. Using the telephone is 94%. So they don't need help for each of these things. The item that may need the most help with would be housework, following by getting to places outside of walking distance, or driving effectively. So if we go back to the test information function, we can see that's why this test information tends to be concentrated at the lower ends of theta, or the mid-range of theta. That's sort of where we see the most amount of variability in the responses. But now take a look at the distribution of theta for this sample. The distribution of theta has one big pile of people at the top. Now this is the ceiling of the test, and there's some 300 people, half our sample about, that is at the ceiling of the test. And then the rest of the sample, there's a chunk of people who are at the floor. They need help with everything. Half the people don't need help with anything. But then in the middle here, you find the people who we might want to differentiate. Some things they need help with and some things they don't. So right around negative 0.5 was our max value of information for theta. And so you think, okay, great, I'm really measuring people well right here in the mid-range of this day-to-day living. And then you look at distribution of theta, and yeah, maybe I'm measuring them well, but there's not a lot of people proportionally that are in the middle there, and that's fine. Because ultimately, the people who say, I don't need help with any of these features, any of these day-to-day tasks, probably aren't going to be referred for other interventions and can get along fine on their own. It's the people in the middle that where you'd really like to be sure what they can and can't do. So this, to me, is kind of the interplay of what you find. A lot of times in data sets like these, you'll find that test information is not at all near where the peak of the distribution for theta happens to be. So here, the peak of the distribution, most people are at the ceiling. And that's fairly common. Some tests are easier than others. And this would be effectively an easy test, we'd say, because ultimately, most of the tasks that people do are capable. They're capable of performing on their own. So they're answering with a 1 of this. Okay. Questions, thoughts, or comments? I'm going to pause while you think about that and type them in. Okay. So I think what I'm going to do is then leave the rest of IRT here. The rest of the slides that you can find on example 5 do the relationship of item factor analysis with IRT models. Is just describing how we go from one to the other, which I think we've pretty much covered. The other part talks about estimation. And bottom line for estimation is that in Levon, we're not using what I think is sort of a gold standard, which is kind of our full information maximum likelihood. We're using something called limited information. But I made the decision in this class to just focus on what we could do with Levon rather than make you learn 18 different packages. And that's just sort of where the state of development for it is right now. I think hopefully in the next couple of years, you'll start to see more and more options to do that. The other thing that you'll find is, I think, coming to be much more prevalent in the next few years is Bayesian information, Bayesian ways of estimating. So let's just leave it like that. Let's just assume that what we get out of our package is approximately where it needs to be to make inferences off of. Then one thing I want to talk a little bit more, what we're doing is something called this weighted least squares. This is slide 78. Okay, could you please use an example and talk about how you use theta to calculate probability and to use probability to determine theta? Well, if you wanted to use theta to calculate the probability of a correct response, you'd use your item characteristic curve. So you plug in your theta, you plug in your A and B value, and out would pop the probability itself. So for instance here, right here are each of these item characteristic curves. So each of the values of theta combines to give you a probability of a correct response with that item characteristic curve that I don't see the function, but basically it's your linear model version of this here. Here it is. We take negative threshold plus lambda times f. So for any value of theta, we put this into a function. And then we convert that to probability using the, this becomes a z-score. So we calculate the probability based on a probit function that talks about the proportion of area under a normal curve below that z-score. So in R, there's a function called p-norm, I believe, that does that. I built these slides and I've forgotten how I do it. But anyway. But for weighted least squares estimation, one of the cool things that happens, there's a couple bad things that happen. You have to make another option for how you do things. One of those options is you have to tell Levon or M Plus that you want to estimate the model using a certain type of parameterization. What happens in this weighted least squares approach is it tries to calculate what's called a polychoric correlation matrix of your items. So there's this type of correlation for continuous for categorical variables that's called a polychoric. If you can calculate that, then ultimately you can do CFA on that correlation. But the key is that correlation is a bunch of, it sort of assumes these underlying variables that don't exist, and you've got to make some assumptions. And the different types of parameterizations lock in those assumptions. So there's a default, which is the delta method. This is what's called by Mutane and N+. And then there's the Theta version, which is where the error variance is 1. The latter one is what we're going to use in all of our class. I don't get too much into the scale of these things because it doesn't really matter too much. You'll get roughly equivalent results between the two. But to convert between IRT and item factor analysis, we use Theta. So what you'll find in my example, if we go down to the Levon portion, is that I have, when I call the SEM function, I use this parameterization equals Theta. So that in and of itself is how we just do that for everything we do in this class. It will be fine. It'll allow us to sort of compare and contrast the numbers that we get out of the output, thresholds and the factor loadings, and relate them to IRT in a more understandable way. The other part that we get with weighted least squares is that the process of figuring out your chi-square is a little bit different, but sure enough, that's only if you're using M+, is it hard. In Levon, if you wanted to compare the difference between, let's say, a 1PL and a 2PL, which I do later on down here. Here's your 1PL. Levon understands the difference already, and this is where it makes it easy. You can use your tried and true ANOVA function. I mentioned this in the last class. The ANOVA function gives you your chi-square difference and your degrees of freedom difference. And these are the numbers that you record. The p-value, again, this p-value represents essentially the probability that you'd, this is sort of like the lower this gets, the more you'd reject the null hypothesis. And the null hypothesis is the model that has more parameters. So in this case, fewer parameters, more degrees of freedom. So the 1PL we would be rejecting in this case, and pretty much every case as well. But one of the other part of, there we go, this is what I mean. All we need to use is the ANOVA function, the end. That was my attempt at stat humor. There we go. Not bad. Next, the other thing we can get in Levon with this is to get versions of local model fit. We talked about in the last class. But the other thing we can get that you cannot get with the full information maximum likelihood is that you have the ability of estimating a residual covariance between a pair of items. Now, this is something I said it was sort of dangerous to do in CFA, and yes, it's still dangerous to do for the same reasons. We don't want to weaken our measurement argument for the trait itself. We don't want it to be daily living and stuff, for instance. But if we wanted to estimate, for instance, a residual covariance between item 1 and item 2, we could go in here and type the name, just like we would with the CFA model. We'd type the item name for the first value and the item name for the second value, the second item in the covariance, and we just hit play. It thinks about it. Uh-oh. What did I do wrong? Oh, it's running the whole thing, of course. But anyway, what we end up, of course, the data is not found. Long story short, you should be able to get this to work, unlike me. Start running this again. There it goes. It's going to take a while. It's going to run the whole thing. Should have learned my lesson the last time. All right. Almost there. Thinking about it. So, how's it going? Nothing like having class crash and burn from home, just like the way it was at work too. I guess the only difference is when I'm done here, I can just go watch TV or something. I don't know. It's coming. It's thinking about it. It's working on it. The wheel is spinning, and there it is. We have output almost what we need. There it goes. A little bit more. So again, what we end up getting here is another estimate of residual covariance. We can end up doing this is actually residual correlation. So if you're doing full information version of IRT, this is not an option that you have. And the reason for that is you're not doing anything that's CFA-like to your data. In the full information version of IRT, you are just dealing with these binary variables directly, and there's no easy way to add a residual covariance to their types of distributions. With the weighted least squares, with this limited information approach, you're not dealing with the variables directly, you're taking correlations from them and doing factor analysis on it, and sure enough, that version of factor analysis has a spot for where you could put a residual covariance. So that should be what's nice. It fits very well with what you already know, what we've already learned in this class. So I think that's the big picture about weighted least squares and so forth. So let me go to, I would like to now, if you have questions, type them in the box, please. I am going to then go to Lecture 6, which is what happens when we have more than 2 outcomes per item. Because that is our last generalization that we're going to get to. Ultimately, we can do lots of things with it. There's, in the big picture, if you have, we've covered 2 types of data that you might have. We've covered continuous, or plausibly continuous, which was CFA. And we've covered binary. And that sort of leaves a lot in between. I know most of you have Likert-type items that would be categorical but not continuous, and certainly wouldn't have multiple or 2 categories per item. So what we're going to do here, though, is we're going to look at the latent trait models for non-binary responses. Now these are, you can have models for almost pretty much any distribution you can dream of, you can have a model for. But we're just going to cover ordered categories today. By ordered categories, I mean we have, when you have a Likert type item, let's say goes from 1 to 5, a 2 means more than a 1, a 3 means more than a 2, and so forth. There are all other sorts of models that are out there, but I can't cover them all in our class. And even if I could cover them all, if we're going to stay in Lavon to estimate things, we cannot estimate anything more than just the ordered categories. But if you're interested in more information about this, do take a look at these slides. I have M+ examples that Lisa had built that are online that you can see as well. But we're going to start with what's called the ordered categories, or the graded response model itself. Because you'll ultimately have, what it ends up doing is it generalizes what we just saw with the binary items in a pretty straightforward way. So I'll start this today. We have about 15 minutes left in class. And then on Thursday, I'll go more into this, and we'll talk about the example that shows up with this as well. But we're going to start with our friend the logit. What we're going to say is that the logit, and in our case the probit, both of these are interchangeable because Lavon uses probits, is also the basis for many other generalized models for predicting categorical outcomes. So we mentioned before that in the IRT for categorical outcomes, the number of thresholds that you would have would be equal to 1 minus the number of levels or categories in the item itself. So for that 2PL model, or for the 1PL, for anything with binary data, we only had 1 threshold. And that was because there were 2 categories themselves. So what we're going to have when we get to this, what we call a graded response model, or what we call a cumulative logit, we will find that if we have, let's say, 5 categories an item, there'll be 4 thresholds we have. But in addition to the 4 thresholds, we'll find that there's actually a set of what we call submodels that show up. And our simple item characteristic curve that we saw in IRTs becomes a little bit less simple because there's effectively 4 different curves that are going on. So let's take a look at these models for categorical outcomes. If you have capital C categories, if we use what's called a cumulative logit or proportional odds model, if we were doing something like in SAS or in GLM and R, what this is going to do is create, with 4 categories, 3 different submodels. And the submodels would basically be comparing a set of category options with another set. So submodel 1 would consider the 0 versus 1, 2, and 3. And submodel 2 would consider 0 and 1 versus 2 and 3. And then submodel 3 would be comparing 1, 2, and 3 versus 3. The way it works like this is these submodels, if we were going to predict up, we could kind of predict one way or the other. Predicting up is what we do in Lavon, I believe. By the way, I always flip the sign of this, so we'll get to there on Thursday. I'm not all here today. The submodel is talking about the probability that an item response is greater than the lowest value. So in case of submodel 1, we would be looking at the probability that a response was either a 1, 2, or a 3. So that's the first submodel. The second submodel is looking at the probability of a response being greater than a 1, so that means kind of a response 2 or 3. And then the third one is the probability of a response being greater than 2. Now again, if we're in logit land, we have this e to the parameters over 1 plus e to the parameters is what we call our inverse link function. But what we're going to find out is these parameters become ordered as well. And you'll see that these are cumulative probabilities. So if we wanted to actually get the probability of being exactly at a 0, we would have to take the probability of being, well, here, let's go down there. The probability of being exactly a 0 would be 1 minus the probability of being 1 or greater. So in this model right here, the probability, this first submodel looked at the probability of being greater than 0, or 1, 2, or 3. We know that the probability, if there were to be a submodel below this, like submodel 0, the probability of being equal to 0 or greater would be 1. Everybody has to have a 0, 1, 2, or 3 of the item. Don't talk about missing, right? Let's pretend everybody has the same data. So that probability of a 0 would be 1, which is the probability someone took the item response, minus the probability of 1 itself. So that's the probability that somebody got a 0 for the item itself. So those 3 submodels can produce 4 actual probabilities. The probability of a 1 takes the probability of being greater, or 1 or greater, and subtracts from it the probability of being 2 or greater. And likewise for 2, the probability of 2 takes the probability of taking 2 or greater and subtracts from it the probability of 3 or greater. And then the probability of 3, well, you can't get any higher than a 3 on the item, so therefore that second probability is down to 0. So that's how it goes. So in our analysis, let's see if I can. Now PowerPoint's reading. There we go. The polytomous models, we tend to have this idea of what's called a graded response. We assume that if we take the IRT model and use theta to predict each of the submodels, we would get this categorical outcome. And the names for these categorical models are widely vary and are all sorts of crazy. The one that we talk about is either the graded response or the modified graded response model. But ultimately, it's predicting a series of categories, and you're doing so in a way that says the categories are ordered in sequence. There are other models out there. The categories may not entirely be ordered, which is somewhere in between, or there's no way the responses are ordered. Nominal response is effectively saying no way the responses are ordered. If you ask a person, for instance, what's your favorite flavor of ice cream, and it was like chocolate, vanilla, strawberry, or other, nobody's going to order those, but unless, of course, you're me, and then the right answer would be vanilla, right? So what you end up getting there for nominal response is sort of the most general, but we're not going to talk about that too much. Somewhere in between is this partial credit or rating scale, which is also weird. So I'm going to just focus on something to hang on to. We're going to deal with greater response models for ordered categories themselves. And again, if you remember what we were doing with IRT, we were taking this idea of a threshold, in this case the threshold at 0, and coming up with this hypothesized underlying response variable. In the binary IRT, there was just one threshold. It was actually the value happened to be estimated. But now, because we have more than one category, we have two thresholds. So if that underlying continuous response is down here, it would be a 0. The actual response would be a 0, be a 1 or 2. I think this takes us away from what we're talking about a little bit. So to do this in Lavon, we do the following. And this is probably too much at the end of class and probably too much from doing from home, but I'm going to say it today. We'll stop here and we'll go on and talk about it again tomorrow, on Thursday. So what we're going to do, let's take a look at this IFA version, which is what shows up in Lavon and M+ right here. If we have an item that has 4 categories, 0, 1, 2, or 3, we're going to come up with 3 different submodels. So this first submodel is for the probability of a 1, 2, or 3, 1 or greater. And then what's going to be equal to is E, or in the logit case, E to the first threshold plus the factor loading times the factor. So again, we form this linear style function, first threshold for the first submodel plus factor loading times factor, to create this submodel that tells us the probability of being a level 1, 2, or 3. Or another way of putting it, 1 or greater. For the second submodel, we put the second threshold. And you'll note, again, we have the same factor value, we have the same factor loading, but our second threshold now shows up instead of the first. So if you were going to plot these, they would look like 2 PL ICCs. The 3 submodels would do like that. The only difference is where they would be located. The center of them would be different, but they'd be parallel curves. And finally, for the third submodel, again, we can form it with the third threshold. So if we wanted to talk about the probability of being in each category, we would find that same probability below, just like I just mentioned before. So let's take a look with the curves themselves. Again, on this plot, we have on the bottom the x-axis theta. Let's say the mean is 0, the standard deviation is 1. And these are the 3 submodels. This pink line is the probability of being greater than 0, so 1, 2, or 3. The yellow line is the probability of being greater than 1, so a 2 or a 3. And the blue line is the probability of a response that's greater than 2. So this is actually the probability of 3. And you'll see these 3 lines look parallel. The only difference is their center, their location, their difficulty. And that difficulty now, you'll see there's 3 difficulties. Because ultimately, if we had 3 thresholds, we can convert those to difficulties in the same way that we had seen those done previously. But difficulty is nice because it talks about the 50-50 point for a person. But now instead of, when in the binary items, the threshold was the 50-50 point of a person getting a 1 on the item. Here, it's the 50-50 point of being what this probability is saying. So in this case, -2 would be you'd have a 50% chance of being greater than 0, but a 50% chance of being at 0. And for the second submodel, a 0, if you had a theta of 0, you'd have a 50% chance of being a 2 or 3, or a 50% chance of being 0 or 1, and so forth. So this is all with the same factor loading or discrimination. They all have the same slope. And if we were to make the slope a little bit bigger, you'd see the lines get steeper between the 2. So you have a discrimination of 1, discrimination of 2. And again, slope, discrimination, factor loading, I'm using those synonymously. So each submodel gets its own item characteristic curve, it looks like. They're ordered in difficulty. The first difficulty has to be less than the second, which has to be less than the third. But if we were to go then and talk about the probability that someone answered in each specific category, not the submodel, but now the probability y equals 0, this would be a graph, or probability y equals 0, or 1, or 2, or 3. Now this graph has 4 lines to it. because there's 4 possible outcomes to the item itself. So the probability of a 0 is this blue curve here, which is sort of the parallel of what the light blue, the dark blue versus light blue. So here you talk about the probability of y equals 0 with respect to theta. The pink line is the probability y would equal 1. The yellow line is the probability y would equal 2, and the light blue line is the probability y would equal 3. And in this graph, what we can do is talk about the ranges of theta where different options are most likely to occur. So for instance, if you have a theta less than -2, right, the most likely option someone's going to choose is the line that's at the top of the probability. So right here after -2, the blue line is the top. So someone with a theta less than -2 will pick the lowest category on the item itself. Now if your theta is between -2 and 0, the pink line is the one with the highest probability. So you're most likely to pick the response of the first or category y equals 1. And then between 0 and 2, again for theta, 0 and +2 for theta, the most likely option you'll pick is y equals 2. And then finally above 2, you get the most likely option of being y equals the highest category of 3. So now M plus will make this plot for you, but I created the function, and Levon won't, but I created a function that would do it, so we'll see that the next time we go forward. Now here's another set of item category response curves. This is probably more what you see in practice. This is one that's nice and evenly spaced and so forth, but here, this one, it tells you there are 2 really likely options. There's y of being 0 and y of being 3. So the lowest option or the highest option. Now the other ones are not necessarily a 0 chance that you pick them, but there's a chance that you could pick those as well. So it's not a great item. Effectively, you think you have 4 categories here, but really you only have 2. And this is the type of item that you might find in like a political survey, something where there's a really polarizing sense of opinion. If you have people who are on the high end of the theta value picking the top option and people on the low end of the theta value picking the bottom option, this could be something where really there is no in between. There's just this polarizing question that you might ask, something along the lines of, which political party, or take a platform plank of one of the political parties and say how well you agree with that, or something along those lines. And so if you take a platform plank from the Democratic Party and you have this 4-point Likert scale where 3 is strongly agree, 2 is agree, 1 is strongly disagree, and 0 is disagree, 0 is strongly disagree, 1 is disagree, then if you give that item to people who are on Republican, you might see this, and when you give that item to people who are Democrat, you might see this. So something along those lines, or vice versa. So it becomes something that you see in a lot of different places. Now, again, we'll come back to this on Thursday, but I just want to make one more note. What does this do for the item information function itself? Well, again, this item information now, because we have these multiple lines, there's sort of peaks in information at where each of the difficulties might be. And so you might start to see information functions that have a lot of wiggle to them. So each of these is a version of a test itself, and each of these items, each of these information curves here. So it's an interesting world. The information function. Typically, with 4 categories, you get more information than you get from a 2-category item if people are using all 4 categories. But the information curve itself, let's take a look at that green curve. There's a little wiggle into it. That is something that describes, it's possible because you might have different values of these B parameters that are clumped in different areas, or in this case, thresholds. So at that, it's 1:15, and I'm going to stop. If you have questions for me, please do send them over email or something along those lines, or you can ask them in class on Thursday. But thank you for participating. I know this is not exactly the best way of doing class, but I think it's the best considering all the other options today, so I appreciate your patience with me, and I hope to see you again on Thursday. Oh, question from Katie. Homework 4. Homework 4 will not be due this week. I'm going to probably set the due date to be maybe a week and a half from Friday, but we'll talk about it exactly Thursday. I'll see what we can do. We'll have a open negotiation, but certainly not due this week. But after this lecture, you should be doing everything you need with it. Anyway, thank you all for your time, but we will talk about Thursday, and I'll make a due date something that's reasonable so we can all get it done and not squeeze it in, okay? All right, thanks, everybody. Take care. Have a good afternoon. Happy Halloween.